In part 1 of our series, we discussed atomic weapons in detail. In part 2, we will discuss the nuances of atomic energy. We will first explore 20th and 21st century popular media pertaining to atomic energy. We will then offer you a case examination of the infamous 1986 Chernobyl disaster in the former USSR, modern-day Ukraine. Lastly, we will discuss implications for the future pertaining to atomic energy. The following footage is a series of excerpts from a famous 1952 American film, A is for Atom. A is for Atom was created with the aim of sharing knowledge of atomic sciences to the American public, particularly children. We selected key excerpts relating to fundamental concepts of atomic energy. We invite you to watch this footage with us now and urge you to think about how it may have shaped public perceptions of atomic energy.
The atomic age was born. There is no denying that since that moment, the shadow of the atom bomb has been across all our lives. All men of goodwill earnestly hope that a realistic control of atomic weapons can and will be achieved. Meanwhile, good sense requires that all of us prepare for any eventuality. But wisdom demands, too, that we take time to understand this force. Because here, in fact, is the answer to a dream as old as man himself, a giant of limitless power at man's command. And where was it science found that giant? In the atom, a particle so infinitely small that it takes over 100 billion atoms to make up the head of a pin. Just as other millions and quadrillions of atoms are the tiny building blocks which make up everything in the world. Now, within each element, or family of atoms, there can be different members, each one having the same number of protons, but differing in the number of neutrons. The total of an atom's protons and neutrons is its atomic weight. Thus, in natural uranium, we have U-234, U-235, and U-238. These different members of the same element or atom family, science calls isotopes. Some elements, tin for instance, have a great many isotopes. Others, like aluminum, are lone wolves with just one. Now, most atoms of most elements are content with their lot in life. We speak of them as being stable, but others are busy day and night, being what science calls radioactive. Like radium, throwing off powerful rays along with some of its neutrons and protons, until it actually alters its own nuclear structure and changes to another family, and then to another, until it does become stable at last. This spontaneous changing of elements is called natural transmutation. Its discovery gave men of science an idea. If an atom could change itself, why couldn't man? That first experiment, others by the thousands followed as scientists devised ever more powerful particle accelerators, commonly called atom smashers, to transmute more and more kinds of atoms. All scientifically important, but hardly world-shaking. Then, in 1939, some scientists were experimenting with transmutation of uranium. What would happen, they wondered, if they fired a neutron at a uranium nucleus, already the heaviest in nature? Why not try? So they tried. And the result? Nuclear fission.
Located in the nuclear core of a fission reactor are fuel rods, moderator and coolant fluid, and control rods. Each fuel rod contains tiny pellets of uranium dioxide. In these hundreds of fuel rods, fission occurs, producing an average of 2.5 neutrons per fission reaction. The fuel rods are surrounded by water, which acts as a moderator by colliding with the neutrons and slowing them to a low thermal level. The water absorbs the thermal energy, which is used to drive a steam turbine to generate electricity. The low-energy neutrons enter other fuel rods and collide with uranium-235 nuclei, creating additional fission chain reactions and the release of more neutrons. The amount of low-energy neutrons present is regulated by control rods made of boron, which are very effective at absorbing neutrons. These rods are raised out of or lowered into the core as needed to sustain the chain reaction at the desired level.
This technology is often heralded as a savior of humanity. The following video, produced by the Russian State Nuclear Energy Corporation, reflects this sentiment in celebration of 60 years of worldwide atomic energy applications. However, we urge you to stop and consider the following. Are productions like these biased? Are fissile materials being kept in safe and secure conditions? And can fissile materials ever be 100% safe? What are the waste products from these applications? And how are they being dealt with? The discovery of nuclear fission in the 1930s paved the road to the developments in nuclear energy. This process was employed by the first nuclear reactor, Chicago Pile 1, which was developed in 1942 as a part of the Manhattan Project. The potential of this technology to supply energy to large swaths of land and populations was realized soon after. As of 2016, 444 nuclear power plants exist around the world in 30 countries. These plants provide approximately 11% of the world's energy. However, nuclear energy is not without its risks. We invite you to explore with us one of the most infamous atomic events, the Chernobyl disaster of April 26, 1986.
На Чернобыльской атомной электростанции произошла авария. Поврежден один из атомных реакторов.
April 26, 1986, the Chernobyl reactor in the Ukraine USSR underwent routine testing. A component of this test required all safety protocols to be temporarily shut off. This resulted in the reactor undergoing a critical meltdown event due to a positive feedback loop of atomic decay. The ensuing explosion resulted in the irradiation of large swaths of Europe and the Soviet Union. A zone of kilometers was evacuated and still remains uninhabitable to this day due to the high levels of radiation. This irradiated zone is also called the exclusion zone, or more colloquially, the death zone. To this day, access is tightly controlled and monitored. The following footage, shot remotely by a drone, shows the abandoned city essentially frozen in time since April 1986.
Despite widespread evacuations of surrounding communities, the Soviet Union refused to acknowledge to outside powers that the Chernobyl accident had occurred. It was not until over a week later that scientists in Sweden noticed abnormally high levels of radioactive isotopes in snowfall during a blizzard. These scientists used meteorological charts to trace the origins of the snowstorm and realized that an ongoing high-level radioactive accident was underway behind the Iron Curtain. To this day, the lands around Chernobyl remain dangerously radioactive. The Ukrainian government is undergoing emergency measures to try and contain the most volatile components, namely the infamous elephant's foot or melted core of the reactor. This object is still belching radiation into the environment, and there are serious concerns that it will melt through the ground and eventually reach the water table. If this occurs, another explosion will happen, contaminating huge amounts of Europe and Asia's freshwater supply. It would be an utterly cataclysmic event.
Thank you. Now we'll pass it to the survivor of the Chernobyl disaster.
Right, so as Aaron said, I was living near Pripyat in the Ukraine when the Chernobyl disaster happened. The background story is basically the scientists were just doing some lab testing and they turned off the safety features, and that led to one of the worst nuclear disasters in history, nuclear accidents. So it was rated as level 7, which is the highest on the scale. 134 workers suffered from acute radiation syndrome and 24 died within weeks after. As well, a lot of children in that area were infected with thyroid cancers because they drank a lot of contaminated milk. So it wasn't just, the effects weren't just the day of or the week of, it lasted for years, and people are still doing studies on the catastrophe. So I'm just here to say that I'm against nuclear power. It does more harm than any good, and I think these deaths and this catastrophe just exemplifies that.
Да. Что у вас там горит? Взрыв на главном корпусе, между третьим и четвертым. А там люди есть? Да. Поднимай над состав. Поднимаю, начальника поднял. Так всех весь офицерский состав, офицерский корпус поднимай. Леонид Алексеевич. Да. Алло, Припять, 3 и 4 блок горит крыша в результате аварии взрыва. Увидел, давай. Не подтвердили, авария там произошла у них. Это диспетчер Припяти сказала. Пожарная охрана. Алло, Иванков? Да. Значит, вы выезжаете в Припять? Алло. Да, я слышу. На атомную станцию выезжаете. Там 3-й, 4-й блок горит крыша. Пожарная охрана. Алло, Полесская? Да. Вы, значит, выезжаете на атомную станцию, там горит крыша 3-го, 4-го блока.
Like other processes, they generate waste. This waste contains radioactive elements. People and the environment must be protected from the potential hazards of such waste, now and in the future. So countries need to manage their radioactive waste safely and securely, and make sure it's kept under control. This responsibility starts as soon as a country decides to use nuclear technologies. And techniques are available to manage radioactive waste. Radioactive elements are unstable and emit radiation as they decay. The decay rate is measured in half-lives. This means the time it takes for the activity of a radionuclide to halve. After another half-life period, the activity is again down by half. This continues, and eventually the material emits only negligible amounts of ionizing radiation. Each radionuclide has its own half-life. So waste can be hazardous for periods of time stretching from a few hours or days up to hundreds of thousands of years. Radioactive waste is classified depending on the half-lives and the level of radioactivity of the nuclides it contains. According to the IAEA's safety standards, there are 6 classes of radioactive waste. Each waste class has different management and disposal needs. Many countries already have near-surface disposal sites for waste with low levels of radioactivity. These facilities can consist of silos in the ground, trenches, or vaults. Once they're full, they will be backfilled with grout or soil, sealed and closed according to their disposal license.
Several nations have recently proposed the creation of deep earth vaults to store radioactive waste for thousands of years. These vaults would be located hundreds of meters below the surface with constant security of the entrances. At first glance, these vaults sound like an amazing solution, but upon a closer examination, we must pose the following questions. How can we ensure that these vaults remain secure for centuries? How do we ensure that a natural disaster will not result in the vaults being breached? How do we communicate to people 24,000 years in the future, which is the half-life of plutonium, that extremely dangerous objects are buried in the vault? What if they assume it's buried treasure? Think about archaeology now. How difficult is it to interpret the writings of ancient Mesopotamia, the oldest writings of humanity? These writings are only 6,000 years old, just 1/4 of the amount of time that radioactive waste will be dangerous, and just 1 fraction of the amount of time that we have to communicate across. How could one warn of the dangers pertaining to advanced scientific theories when language and symbols may not be the same, and records of the site may not even exist? However, there are alternatives. Renewable sources such as wind and solar energy offer safer alternatives to our growing energy needs. We urge you to write to your families and friends, the media, and your politicians. Demand alternatives to nuclear energy. It is not just your safety in question, but the safety of countless unborn generations.